Hi friends, this is the second part of statistical inference, in which we are going to consider mainly the analysis of variance and its core concepts, along with a SAS example of one-way analysis of variance. In the previous session on statistical inference, we have seen that we can test the hypothesis of equality of two means versus three different types of alternative hypotheses. So, in that situation, we were considering one treatment drug against one active control. So, we were considering only two arms. Whenever there are more than two arms, for example, suppose there are three treatments which are being compared with one active control, or there are four treatments to be simultaneously controlled, to be simultaneously assessed for their efficacy. So, we consider the analysis of variance for testing these multiple treatments hypothesis. The null hypothesis in analysis of variance is always the homogeneity of all the treatments. If there is only one factor, for example treatment, and we are comparing them among all, then we are into the one-way analysis of variance. So, one-way analysis of variance is used to simultaneously compare two or more group means based on independent samples from each group. If there are more than one factors, by factor I mean, for example, if you are considering the geographical regions along with the treatments and you want to do the analysis, then you can perform the two-way analysis of variance, and there can be three-way analysis of variance or multiple analysis of variance also. We will stick to the one-way analysis of variance and try to understand the concept behind that. So, there is one factor which is dividing the population into different groups. We are considering the variation among the sample group means relative to the variation of individual measurements within the groups. So, greater the evidence that the hypothesis of equal group means is untrue. So, we are talking about the multiple treatment scenario, and we are trying to test whether all the treatments are alike, all the drugs behave alike. In clinical trials, this analysis of variance method might be appropriate for comparing mean responses among a number of parallel dose groups or among various strata based on patient's background information such as race, age group or severity of disease. So, drug group or drug can be considered as one factor, another can be considered as race, third can be considered as group, and the more and more factors you include, then the dimension of the analysis of variance increases. Right now we are going to consider only one factor, suppose that is treatment, that is drugs. So, the assumptions behind analysis of variance are as follows. The populations from which the samples were obtained must be normally or at least approximately normally distributed. The samples must be independent and the variances of the populations must be equal. So just as we had the assumptions for conducting t-test for two sample means, these are some assumptions which we have to make before doing the analysis of variance. Now, the first assumption of normality is generally satisfied if you have large samples due to the central limit theorem. The second assumption is satisfied if these are different treatments given to different people. So, different drugs given to different groups, then there isn't any question of dependence between the outcomes. And the third assumption is that the variances of the populations must be equal. So, that is an assumption regarding the intrinsic behavior of responses by the patients among all the groups. So, the way in which or the dispersion for each of these groups is assumed to be the same. As I have said, the null hypothesis is that all the population means are equal. And what will be the alternative hypothesis? Negation of this statement that all means are equal is not that all means are not equal, but at least one mean is different, then this null hypothesis is not true. So, H0 is that all populations means are equal and H1 will be that at least or some of the means are different. The technique of analysis of variance first of all computes the grand mean from the entire data. So, you have in all n observations which are there coming from say k number of treatments, then you combine all of them together and find out the total of all these observations and divide by capital N, then you get the total sample. You get this grand mean, that is overall mean in the data. Now, the idea behind the analysis of variance is as follows. If your observation is denoted by x and the grand mean is denoted by x bar gm, then you take the deviations of each of these observations from the grand mean and take the square and the total of these squares, then it is nothing but the sum of squares of the deviations. So, this is the total variation, how far each individual observation is away from the grand mean. So, this is the total variation in the data. The factor which you are considering in one-way analysis of variance is classifying the data into number of groups. Suppose there are k treatments, then there will be k groups. So, the total variation, this one, is split into two components. One component is known as between group variation and the other component is known as within group variation. Between group variation gives us an idea about how the treatments are causing the variation among the different groups, while within group variation gives us an idea about the variation within every group and overall within variation. I am not purposely not giving the formulae for these two components here because we are interested in knowing only the concepts. So, what is known as between group variation? The variation due to the interaction between the samples is denoted as SSB, the sum of squares between groups. There are k samples involved with one data value for each sample, the sample mean, and so there are k minus 1 degrees of freedom. The concept of degrees of freedom is little difficult to understand. I can tell you one simple example. Suppose you are asked to give me 4 numbers so that their total is equal to 100. Then how many numbers you can choose at your will? You can choose at your will 3 numbers because the sum has to be equal to 100. Therefore, the fourth one gets automatically fixed. If you suppose choose 25, 20 and 15, then 25 plus 10, 35 plus 15, 50. So the fourth gets fixed as 50. So in that case, the degrees of freedom for choosing the numbers will be 3 and not 4. Some such similar thing happens here, and then if there are k treatments, then whenever you write down the theory for the analysis of variance, you can demonstrate that it has the k minus 1 degrees of freedom. Let us not go into the technical details of that further. The variance due to the interaction between the samples is denoted by MSB for mean square between groups. This is the between group variation divided by the degrees of freedom. So whatever you compute here as the sums of squares between group sums of squares, you divide by the degrees of freedom and you get the mean sums of squares for between the groups. The within group variation is also known as sums of squares within groups or error sum of squares. So this is due to chance. This is not being attributed to the treatments, whereas the between sums of squares or the corresponding MSB is attributed to the variation due to the treatments. So the variation due to differences within individual samples denoted as SSW for sums of squares within groups. The degrees of freedom is equal to the sum of the individual degrees of freedom for each sample. Since each sample has degrees of freedom equal to 1 less than its sample sizes and there are k samples, the total degrees of freedom is k less than the total sample size, and therefore degrees of freedom for error or within is equal to n minus k. The variance due to the differences within individual samples is denoted as MSW or mean square within groups. It is also denoted as mean square error. So this is mean square error is again the sum of squares divided by n minus k. Here you will only have to understand the technique. We cannot go into the theoretical details why it is so, and we cannot answer these questions like what is the rationale behind using this F test in such a short span of time. So basically you, after computing this MSB and MSW, you take the ratio of mean sum of squares between divided by mean sum of squares within, or also known as mean sum of squares error. The degrees of freedom for F test statistic, which has got 2 degrees of freedom, which are also called as parameters of the F distribution, are k minus 1 and n minus k. This is a famous analysis of variance table. You have the source of variation, which is between treatments and within or error. Then the next column is degrees of freedom. The total degrees of freedom is n minus 1. N are the total number of observations. K minus 1 are the degrees of freedom for between. So if you are comparing 4 treatments, then this will be 3. And if you have suppose 60 observations, then this will be 59. So this will be 59, this will be 3, and then you can obtain these degrees of freedom by subtracting this value from this. So it will be 56, which will be also 60 minus 4. So in this way you compute this column. Then the between sums of squares are computed, total sums of squares are computed, and if you subtract these sums of squares from total sum of squares, then you get the sums of squares within. So subtracting this quantity from the lower value here will get you the value of within sums of squares or error sums of squares. Then you divide to each of the sum of squares by the respective degrees of freedom. So SSB divided by k minus 1 is mean sum of squares for between treatments, and SSW divided by its degrees of freedom is the mean sum of squares for within. You find the ratio of this MSB divided by this MSW. So this quantity divided by this quantity gives you the value of F, which is our test statistic, which will be compared with the critical value of the F distribution. Or we will compute the p value and will compare the p value with the level of significance alpha. The decision will be to reject the null hypothesis if the test statistic from the table is greater than the F critical value with k minus 1 and n minus k degrees of freedom. So when you are comparing critical value of the test statistic, you reject whenever your observed value is greater than the critical value. Otherwise, you accept the null hypothesis. If the decision is to reject the null, suppose we reject the null hypothesis. What was the null hypothesis? That all the treatments are homogeneous or all the treatments are behaving alike. Then at least one of the means is different. So they are not equal. So at least one of them is different. That is the conclusion out of the analysis of variance. However, the analysis of variance does not tell you where the difference lies. For example, if you are comparing 4 treatments, four drugs at a time, and you reject the null hypothesis of analysis of variance, then what would you say? That all of them are not equal. At least one of them is different. But which one is different? That answer cannot be given by conducting only the analysis of variance. For that particular answering that question, one has to either consider the Shafi's test or Tukey's test, which is right now beyond the scope of this module. Let us consider an example and use SAS to understand the analysis of variance. A new serotonin uptake inhibiting agent, SNX95, is being studied in subjects with general anxiety disorder. So GAD is the response. 52 subjects diagnosed with GAD of moderate or greater severity consistent with the diagnostic and statistical manual were enrolled and randomly assigned to one of the 3 treatment groups: 25 mg of SNX95, 100 mg of SNX95 or placebo. So we are having 3 treatments. One of them is placebo and other 2 are the serotonin uptake inhibiting agents with different compositions. Here we are administering only 25 mg and 100 mg of the, here 100 mg of the same drug. So we want to see if there is any difference among the three treatments using the analysis of variance. How many subjects were given these three treatments? 52 subjects were given these treatments. After 10 weeks of once daily oral dosing in a double-blind fashion, a test based on the Hamilton rating scale for anxiety was administered. So, we have to study the general anxiety disorder. These are the treatments that we are giving. So, what is the response that we are going to have? We are going to have the response as some score of anxiety, rating score for anxiety, which is known as HAM. So, this test consists of 14 anxiety related items. For example, anxious mood, tension, insomnia, fears, etc. Each rated by the subject as not present, mild, moderate, severe, or very severe. So, most of the times it is not very easy to measure the response. You have to use some such kind of mechanism, some such kind of rating scale to measure the responses, especially when it is a study on the psychology of the patient. Because you cannot quantify the stress by measuring only one value of the response. In case of studies like blood plasma levels, etc., you measure the glucose level and that's it. But here you have to take into account several such observations, and the response is quite a complicated value that you have to do something to observe the response. So, this was done, and this HAM-A test scores were found by summing the coded values of all 14 items using the numeric coding scheme of 0 for not present, 1 for mild, 2 for moderate, 3 for severe, and 4 for very severe. For each of the previous ones, a patient will give you the answers like I have mild headache, nausea not present, likewise. So you will code them by 0, 1, 2, 3, etc. and then take the total of all these values, and that forms your response variable. So this is the HAM-A is the response that we are observing among the three different groups. So low dose, that is 25 mg of the drug, high dose 100 mg of the drug, and the placebo were to these patients, none of the medicine has been given. So if we look at the data, 21, 18, 19 not available, so it's a missing observation. We are going to see in our last and concluding session what do we do with the missing observations and all. So here are the observations of the scores HAM for 25 mg group people. How many have been given? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So in all 17 people have been administered 25 mg, of which you have no observations on 2 of them. So in all 15 observations are present for low dose group. Likewise, you have some number of patients with 100 mg, some number of patients with placebo. Now, here I would like to explain to you what is meant by that within variation and between variation. Because otherwise it is difficult to understand the concept. When we look at the data, see, even though each of these patients is receiving the same medicine or the same quantity of the medicine, their scores are different. Here 21, 18, 19, 28, 22, 30, etc. We have learnt about dispersion in our initial sessions. Which is the crudest measure of dispersion that we have learnt? The range, right? So the range of the values here in this case looks like that the minimum is 18, yes, minimum is 18 and the maximum is 35. So 35 minus 18, that is 17, is the range for this group. So this gives you some idea about the variation within this group. So that is within variation. Similarly, here the range is from 16 to 33. 16 to 33. So the upper value seems to have come down by 2. The maximum value has come down by 2. So is it because that we are increasing the dose quantity? That's worth seeing. Anyway, so the range is from 16 to 33. Here it was 18 to 35. And here in case of placebo, it is the minimum value itself is very high because these people are not getting any medicine. So 19 is the minimum value and 37. 19 is the minimum. So this is within that, but within group variation. What we talked about is the within group variation. And how would you find out the between group variation? You can find out the mean for this, mean for this, and mean for this. And then suppose you see how the arithmetic means differ from group to group. From this treatment to this treatment, for this treatment to this treatment. Then you are talking about the between variation. Okay. So that is the concept of the between variation and within variation. So, if the between variation, one thing is clear, that if the between variation turns out to be more than the within variation, then you would say that they are behaving differently. The treatments are causing the responses, or the average responses are different from each other. So, it is as good as the extension of two means test. See, suppose we would have only these two samples, this sample and this. Now forget about this. Then what will be your null hypothesis? Mu t equal to mu c, or mu 1 equal to mu 2. So you are in the two sample situation, two sample means situation. Here you have got third treatment, so it will be mu 1 equal to mu 2 equal to mu 3. That is your null hypothesis. Anyway, so let us see the SAS code for this analysis of variance. First we sort the data by the variable, by dose group. We run the proc means, and then this is the statement which is doing the analysis of variance, which is proc GLM, data is equal to GAD. You are also drawing the plots, box plot, and model HAMA, which is the variable, over the dose group. So dose group is the factor. If you would have had two factors, so it will be two-way analysis of variance. So one more variable will be added here. There are some two other statements in this SAS which we will not bother now, which is doing some other multiple tests. So let me go to, I have run this code for you, and then here you find you get to see the output of the SAS code. There are three levels of dose group because there are three treatments. Number of observations read were 52, number of observations used were 48 because there were some missing observations. This model is nothing but the between treatments. Error is the within that treatment, within the groups. This between groups, within groups, they have the same meaning but different terminologies for in this ANOVA. The procedure that we have used, SAS procedure, is proc GLM. Then it gives you the sums of squares. Total sums of squares are here. This is the model sums of squares or SSB in our slide. If you subtract this from the total, you will get this. This is error sum of squares. You divide this quantity by degrees of freedom, you get the mean sum of squares between, mean sum of squares within by dividing it by this, and then you take the ratio of these two and compute the value of f. So the value of f is 6.97. This is the test statistic for analysis of variance. So you can decide your conclusion on the basis of this test statistic, whether it is greater than the critical value or it is less than the critical value of the F distribution. Here SAS is giving you the p value, probability that greater than your observed value. So it is 0.0023. So what would you suggest? Since this value, p value, is far less than the level of significance 0.05, you are going to reject the null hypothesis. Okay. So the same is been printed here so that you will have it in your notes. This is giving you the box plot. So idea about the variation in the three groups. So here this is the high dose group. I have explained you the ranges, different ranges. So the range for high was quite small. So this is the minimum, this is maximum, this is the median value, this is the value of mean. This way the box plot is drawn, and then here this is the minimum and maximum, and you have here Q1, Q2 and Q3. These are the quantiles and this is the arithmetic mean. So the more wide that particular box is, the more is the variation. So in yellow the variation is large as compared to high and the placebo group. So this is 6.97 printed here, the one which we saw. How to write the proc, that has been explained in this slide. The summary statistics are first obtained for each dose group by using proc means. It's not necessary though. You can directly use the proc GLM. In this example, the model factor is dose group. So variable is equal to dose group. Must also be specified in the class statement. The output shows the MAC, the MSG and the F test for the dose group. The p-value is 0.0023, indicates that the mean HM scores differ significantly among the dose groups. The critical value, if you look at the critical value of F, then it is 3.2. So this also, since this is greater than 3.2, we reject H0 and we conclude the same as we concluded on the basis of the p-value. So the conclusion is that there is a significant difference in mean HM scores among the three dose groups.